Now let's get ready for qubit energies in a ion electronic states. What does electronic states mean? Well, they're electron levels, energy levels. And this is one of the things that brought quantum mechanics needs to the atom itself. So there are spectral lines that can be seen, and the spectral lines are sharp and distinct, meaning that not all energy levels exist in the ion. That's kind of the history of it. So the last part with the harmonic oscillator, the wiggling of the ion, that might have got you pretty much out of whack. Well, today it's going to be a lot easier because we only have two energies, and the energies are already figured out. Hey, nice. I like that. The energies are already figured out. So let's start by looking at the script. An ion, like, I think that's ytterbium or californium, has many internal energies levels due to its electron configuration, meaning you've got a whole bunch of electron states that are there. So the whole kinds of electrons that are in there at different energy levels and so on. Now, why those two are chosen, I don't know right now. But they must be the ones that work right. So anyway, here is the 0 and the 1. 0 and 1, that comes from binary computers, like the traditional ones. And here we're going to say that 0 represents the G, or the ground state, whatever the energy is there, and 1 equals an E, which is the excited electronic state, meaning you have an atom here and it can be excited up to the next electronic energy level. Excited, how is it going to do that? What's going to excite it or energize it? That's going to be a laser, a very fine-tuned laser that can be down to the dimensions of an atom or even less. So that's a little wild, but technology today is wild. So let's go back to what we saw in, let's go back to this thing called the time-independent Schrödinger equation. And if I can get that on the screen right. Okay, there we go. Look, here's the Hamiltonian. There's the function, just like we talked about earlier. And there's the function again on the other side. And there's the energy value. So all we have to do is find a Hamiltonian that when you multiply it times this function, you get the energy value times that function. Now the Hamiltonian, oh my gosh, that's complicated. It's p squared over 2m. It's all this stuff. Well, but we already know what the energy is. We already know that the energies are measured by the spectral lines, so we can already calculate that. And here's our Hamiltonian. How easy could it get? E0 is here. E1 is here. Why? Why are they in this form, and why is this a matrix? Well, it turns out that the Hamiltonian can be represented by a matrix, not just a differential equation. Matrix sounds a heck of a lot easier than a differential equation. So if we can get it in a matrix form and it's easy to get there, let's by all means use it. So here's another way. If these two energies differ by a fixed value, then we can just plug in a 0 here and plug in the difference value here. And that's exactly what's done here. Energy is 0 here. The energy for the excited state is h bar. There's that Planck's constant again, times the frequency. Frequency of what? Oh, I bet that's the frequency of the light seen in the spectral line. So if we take the frequency seen in the spectral lines, take that frequency, multiply by 2 pi, you get the radian angle or radial frequency, and then you get the energy. So, okay, are we done yet? Not quite, because we have to define this function sub n. Here we go. Do 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 do. Do 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 do. Okay, here's two functions. One for the 0 and one for the 1. Now it's even looking simpler. Here's just a simple column vector with 1 at the top to pick out the 0 energy and a 0 at the bottom to reject the excited energy. This one does exactly the opposite. It picks out the E1 energy level and rejects the E0 energy level. Let's go on. Let's see what's going on here. Where do we go? Okay, I think that's it. That is it. So if you took this matrix, multiplied by column 1 over 0, then you'd multiply this row times the column. That would be the first element of the vector, which would give us E0, and this times the 1, 0, the 0 and the 1, I worked this out on paper. Maybe I don't need to do that. Maybe this is the shortest video on record. I'm not sure. But anyway, let's see if we've covered everything. How about a laser interaction? And let me squeeze my picture down a little bit so we can read it. Would you like now to introduce a laser interaction and solve the time-dependent Schrödinger equation to see how qubit states evolve dynamically? That's the end of this video. Do you like a short one? Well, this was a short one. Now the next one is a mess. Look at that mess. Look what we got to do down here. We're back to differential equations. So that's it.